Hi everyone, Architecture Operating Systems. We are in the last series of lectures about operating systems. And in this week, I'm going to introduce the operating system and a brief history of that. Operating systems like Windows and Linux or so many other types of operating system were not like the ones that we are using them at the beginning of emergence of the computers. In 1940s, when the computer came to exist, we didn't have such called operating system, and the person who programmed the machine was in charge of to translate the program to the hardware. So they had to use the switches, the gates, and so on to run a program on the hardware. It was a hardware programming, and the programmer physically had to do this. So the programmer did everything that an operating system does today. So he was in charge of running a program on the hardware. But it wasn't good. In the 50s, 1950s, some changes started happening. One of them was to have someone between the programmer and the hardware, as called operator, or what we call these days an operating system. So the operator used to use these cards, stiff cards, and punch them based on the verbal commands and instruction getting from the programmer, and then place them into the machine, to the computer, which could read and interpret by it and run the program. The operator acted as a human interface between the programmer and the hardware. And as you see, this was the way that they did at that time. But again, that wasn't good. Why? Because having a human in the middle as an operator will cause a lot of delay, and we can expect putting the cards, removing them, and so many other things that can happen to the human actually brought the efficiency of the machines very low. So instead of giving verbal commands to the human operator, at that time, the programmer punched the instruction on the control card, which were inserted at the appropriate place before and after the program cards and the data cards. So it was up to the programmer to write the program in a language and in a way to actually punch the card that put it inside in the machine, and the computer understand and interpret that. So the step in 1960 was to remove the human, and that was up to the programmer to translate the commands to the cards and then to the machine. Again, it wasn't efficient enough. In late 1960s and 70s, it was the first attempt to provide interactive use of computer and operating system that we have at this time. So what happens was that they started thinking of having a program in the middle, write a program in the middle that be very interactive by the user and the programmer, which can introduce and interpret the instructions to the machine. So the computer users found that program, and what happens was that they started, and because the programs started getting larger in terms of the size, so what they had to do, they had to put the program into the chunks, create a program as an operating system that actually translate that to the machine. But because the programs were starting getting bigger and bigger, they had to put it into the chunks that the programs could be placed into the machine's memory to be executed, fetch and executed. So by that time, we needed larger memory because the programs were getting larger, and the solution was putting the program into the chunks. Actually created another challenge for the operating systems to time share or time sharing the instructions. So by at that time, they had to chuck the programs into the pieces, and by the management of time sharing between these instructions, they could run the program. But the issue of protecting one program from the other became more and more important. So that was the story that the operating systems came to exist at the way that these days we use. 1980s, networking came to game, and we wanted to be able to get the machines to talk to each other, send the stuff to the printer and print it. So we wanted an operating system in the middle to help for networking. 1980s. And in 1990s, actually we moved to open systems. In the previous one, when they wrote a program operating system, it used to work for specific hardwares. But from 1990s, we wanted to have a general operating system that they could be used for any hardware platforms, for any hardware that we wanted. So there was a move to build general operating system which will run on any hardware like Linux. So from 1990s that we have Windows, and actually this trend started, and nowadays we use very complex operating systems that can work and helps us to communicate with the machine. So what is an operating system? That was a brief history of operating system. But what is operating system? As we said, we've got a user, we run the program, and or we use the application programs. So what we want to do, we want to translate this program to the hardware. This is operating system job. At the beginning, as I explained, there was someone here to help us to translate this stuff to the hardware. But nowadays, there is a program here that can help us to do the job. Instead of a punch card, instead of someone in the middle, it's an operating system, is a program that can help us. So the operating system itself is a program which is written, compiled, tested, and debugged just like any other program. This program is run whenever the computer is switched on. It's almost always done automatically. No special command is required, so user may not be aware that it's happening every time they switch on the machine. It stays running all the time until the machine is switched off. Operating system is a software which makes the hardware more useful and more user-friendly. So as you see here, the operating system is a big program, is a complex program that acts in this level to translate the programs, the applications, whatever, to the hardware, because hardware works based on binary numbers. We know how computer works, we know how ALU works based on bits, 1 and 0s, and this is operating system job to translate it to the binary stuff and get the programs running on the machine. So what does operating system do? Loads of things is done by operating system. Provides an environment which helps the others to do productive work. Without operating system, you cannot do loads of the stuff that you do these days with the machines, because it provides a friendly environment, helps a user to develop and run programs by providing a convenient and user-friendly environment. Start and stopping the programs and sharing the CPU between them. This is operating system job to get a program start and finish it, or while you are running a program, helps to run another program parallel to that. Most important, managing memory. We use memory, and in the memory lecture, I explain how memory works. We've got different places there. So who will manage that? We use random access memories. So randomly we assign a memory to instructions to the memory. But who will do the job? This is memory's job. This is the operating system job to do the memory management. We will discuss it in more details. Provide mechanism by which programs can ask for more memory or give back memory they no longer need. Input output covers up the difference between the alternative makes and models of devices. Overlaps input and output with processing. So when we install Windows, for example, on a machine, we don't care what hardware you're using, what graphic card you're using, what type of RAMs you're using, what make it is, what brand it is. Why? Because this is operating systems to bring everything on board, to utilize them. In the same time, use different types of inputs and overlap between them, and also process the output. All of them is operating systems job. File system organization. Now, for example, you want to save some of your musics on drive D, movies on drive E, for example, on your hard drive. Who helps to do that? Who helps that for the next time when you want to retrieve and get access to those files, you know where it is, just click on a couple of folders and get to the file. How? This is operating system works in file systems. Protection. You've got one memory, one CPU. I know that we use multiple cores, but in a machine, we've got memory and CPU. Protect programs interference. So there is no issue when you run a couple of programs on a machine. Networking. We use different types of machines on different parts of the world, but we don't care about what sort of hardware you're using, because the operating system helps us to cover up the differences between these machines, and we can communicate. And last one, error handling and recovery. We use Windows, for example, and we get every now and then an error that something is actually going wrong here. I can repair that. You click on the repair and it fixes the problem. And it helps you to run the machine and your program healthier. So this is error handling recovery aspects of the operating system. So I explained that we have user and we've got application program and we've got operating system. But don't forget, GUI for the Windows, for example, that we have, or command interpreter in the Linux, they are not the exact operating systems. No, they are applications will sit on the operating systems that we can communicate with the operating system. They are itself applications. So application program like Excel, for example, or Word, is the same as the GUI that you use or command interpreter that we use in Linux or in the Windows. So all of them are application. And what happens? They use system services to be able to access to the operating system, and from operating system, access to the hardware that we want. So system services are the set of functions provided by an operating system to enable a user to request service from it. So all of them helps us to request service from the operating system. These GUI, when you drag and drop, what happens in GUI, you send a request using the system services, send a request to operating system to move the files. So don't forget that GUI and the command interpreters are in application layer. So we know that in the user space, user process application programs we have here, and we've got hardware in the lower layer. Our operating system is in the middle. Operating system, as we discussed, is a program that helps these two parts to talk to each other. But how operating system works? The heart of the operating systems, there is something called kernel. There is a program, it's kernel, which is very important. Let's talk about that a little bit. What is kernel? Kernel is the central component or heart of the operating system. It is an interface between the hardware components, CPU, disk, memory, whatever, and the software. Is between these two. Makes software to interact with the hardware to get a specific task done. So when you send the request, or we call it a code, when a software wants to get access to a specific part of the memory, this kernel helps to actually provide the resources for that specific program. This is kernel's job to decide the amount of resources, RAM, GPU, CPU, whatever, to be used by every single application. It's the brain of the operating system. It decides on what programs to be executed and on what order. If you, as I said, if you cut the program into the chunks, It decides which one go first, which one go next, how much memory should be allocated and assigned to a specific process or program. It has separate space on the memory, so it functions independently. It works independently. It doesn't mean that it cannot have access to the enough memory that it needs because it's a program itself. So it has a separate space on the memory. It acts as a central authority which guides memory and keeps on all the hardware and software data flow. And what happens is that in this case, when you run a program, it sends a system code. Every process, when you want to run it, they send system code. What is system code? Every process which starts on the system demands the resources from the kernel. When you want to run a program, it sends the system codes and send it through the kernel, and then in actually suitable and appropriate memory, disk, CPU, whatever will be allocated to that using the system calls that we have from here. So we've got two spaces here, user space and kernel space, and we've got two modes, sorry. One of them is called user mode. As you see here, user mode is what here. So when you run a program on a user mode, you won't have direct access to the resources here. So in the user space, only a certain amount of instruction can be executed without having access to the CPU, without getting permission, like add, subtract, and so on. If a program executed in a user mode, it doesn't have access to memory, hardware, and such resources. So because it's running this space. But we've got another mode, which call it kernel mode. This in the kernel mode, if anything is running in the kernel mode, it has direct access to all the resources. The CPU can execute all of its instructions, including extra privileged instructions. If a program is executed in the kernel mode, it has direct access to the memory, hardware, and such resources. So if you run a program in the kernel, you have direct access to that. But we usually run the programs in the user space, and when it is required, you go through the kernel and get access to that. Normally, the machine runs in a user mode. When it wants to do something special, it has to change into the kernel mode. It has to go in the kernel mode and then access to the hardware. So, user mode, as you see, applications are here and the hardware here. Kernel mode is all the operating system, is the brain is there. So based on the kernel mode and user mode, we've got two different types of kernel. If all the files, all the operating system, everything is in the kernel mode, as here, we call it monolithic kernel. But only a small part of the operating system is there in the kernel, we call it microkernel. So monolithic kernel, user services and kernel services, both of them are kept in the same address space. Entire operating system in the kernel, entire operating system is in the monolithic kernel, is in kernel mode. Larger than microkernel, as you saw, less access time because everything is here. We have less access time. You've got access to everything. You don't need to actually go out of the kernel mode to get access to anything else. No, everything is here. Hard to extend because everything is here. It's hard to build on that. But because everything is here and the access time is very low, it's very high perform. It's got a very high performance. And the probability of having crash is lower, but if you have a crash in the kernel mode, the whole system will crash. Linux is very efficient. Why? Because it uses a monolithic kernel. In the Linux machines, everything is here. And it's faster, it's quicker, and because everything is in the kernel. But the other one, microkernel, user server and kernel services are kept in separate address space. They are different. Smaller size, as I showed you, a smaller size. Only a certain part of the operating system is in the kernel. Greater access time, if you have access to something, you've got to actually go out of that. So the access time is higher and slower, but it's easier to extendable because you can build on that. Lower responsibility because not everything is in the kernel. And Windows machines use hybrid. It means that Windows is something between these two. So Windows use the hybrid, macro and monolithic, but Linux use only monolithic kernel. So that was another type of kernel, and let's talk about the different type of operating systems. We've got different types, mainly 3 types of operating system. We can have more, but the main thing is that it depends on the type of the usage, on the requirements of what you want to do. If you want to run a program and you don't need any intervention, we go for batch system, or we have interactive systems, operating system, and also general purpose systems. Let's go over them quickly. As I said, the earliest operating systems, we didn't have any interaction with that. As a programmer, you gave all the instruction data, which call it job. You give the job to the operating system, and it runs that without any interaction or very little interaction between users and the executing program. Like what? Payroll processing, bank credit card. You don't need to interact with that because the operating system should actually run the whole thing and give you the output. No need for any operator or interaction once the job has been started. So for some specific requirements, we use batch systems. But interactive systems is the most common thing that we use. We can interact with the operating system, mouse, keyboard, screen, whatever. And it's an improvement to the batch system because the intervention, you can run, you can stop the program. But in the payroll processing, for example, maybe you cannot stop the program. For the bank, you cannot stop. And it works into the single and multi-user, for example, Windows 10 and Linux, Unix, whatever, all of them are the multi-users, and multi-people can use, the multi-users can use the operating system. And in older one, we had single users, only one machine could use that, like MS-DOS, Windows, and so on. But they were interactive. Also, we've got general purpose operating system. It's a bit of everything. For example, you wanted to have both batch system in some parts and interactive in some parts. It's called general interactive. It's called general purpose operating system. For example, time sharing system may support interactive user, but also include the ability to run the programs in batch mode. So it depends on what we wanted. So in that case, for general purpose operating system, we've got 2 types of them: network, distributed, and special. Network for sharing. You write a program, like for example, Windows Server. We had Windows NT before, but we don't use that anymore. That the main purpose was for communication, for the networking. So that was specific type. We had a specific type of network. Distributed system. What is distributed system? For example, you run the machine on, you run the program on multiple machines, and when you see, when the system sees that one machine is idle, it can actually share the load. The most recent development in the operating system meeting the requirements of the multi-user system. Essentially, it consists of a group of machines acting together as one. Distributed system for running the huge programs. When a user starts a program, it may actually run on the local machine, but if the computer is heavily loaded and the operating system knows that another machine is idle, then the job may be transferred to that idle machine. Cloud computing, when you run a machine, when you run on the cloud, we use this distributed system, and we should have a specific type of operating system for this type of job. And the last thing is the specialist system, dedicated to the processing large volume of data, which are maintained in an organized way, such as real-time operating system, bank system, or so on. Again, it depends on the type of the things that we want to do. We design or use a specific type of operating system. Because of that, we have a number of operating systems, and based on the need, we use the right one. So, operating system is a very large piece of program. How it works, how you should design that. What is important? We need to know what are the main things that operating system does. The main functions is process management. When we put the programs into chunks and we want to run them, so this is operating's job. actually to monitor how to run a program. It's called process management. How to use the memory management, input-output management, file storage, and network management. These are the most important things that we need to know about the operating system. And from another view, we've got modular races, that memory manager, process manager, network manager. As you see, all of them will be in here in this layer, input, output, disk drives, and so on, which actually helps to work with the hardware. And also from the other side is the system service that we discussed. This is called the modular operating system. And later on, we will discuss in the next lecture, we discuss about the process manager, memory manager, and the algorithms that they use to run the programs. So this is the reference book, and all the materials are on the Moodle. Thank you very much, and see you later.